So today I want to talk about Kirchhoff's law. So today our lesson is on Kirchhoff's law. And so there are two laws which I want to go over, which are the current law and its voltage law. And then at 3 I want to, of course, solve some problems. Okay. Simple enough? We'll go with that. Now, earlier we discussed how to do a problem with like one loop or one circuit. So, for example, I have a battery, something like this. I have a resistor, and resistor 2, something simple like this. We'll call this R, we'll call this R, we'll make this U. And in our first situation, to analyze these things, we first analyze the fact that these two are in series with each other, so that R and R in series. That implies that your total resistance is twice R. And so we would replace it in, this is R total delta U. And of course from here we'd obviously solve for the current. And so I total is equal to U divided by RT. And that's simple enough. But what happens if we have multiple loops? What happens if I decide to be a jerk and throw this on an exam? Call this U1, call that U2. Not to be confused with the band, we'll just make all of these the same. Just to make my life and yours easier. What happens if I have this situation? What do? I have two loops. I can use certainly the things that we learned about parallel and series circuits to simplify this, but but I can't do much else other than that because I have a couple of batteries in here that have screwed everything up. So what do I do in this situation? This is where we use principles called Kirchhoff's laws. Okay. They apply to these really complex circuits which don't simplify after you do your series and parallel resistance. Okay? Now, so Kirchhoff had two laws. The first one is, of course, the current law. And you may ask, why am I going over the current law first, even though most textbooks have the voltage law listed first? Well, the reason why I'm doing the current law before I do the voltage law is because basically the voltage is dictated by its current. So the voltage is dictated by the direction of the current that I choose. Okay, so let's start off with what the current law states. Okay, so Kirchhoff's current law, KCL for short, states that the sum of the current going in equals the sum of the current going out. At a node or junction. Okay. Let's go back to my example right here. Okay. How do I know what a node is? A node is where 3 or more wires come together. So I'm going to put that note in here for you. So a node is where 3 or more wires come together. And it can be as many, it can be 3, it's 3 or more. It's 3 or more. But most of the time we just work with 3 because it makes our lives easier. Okay. I could be a real jerk and make something real example. So in this situation here, what does that mean? I have to use blue for current because blue is my favorite color. So what that means, what that means is at a node where 3 more wires. Here's wire 1, here's wire 2, and here's wire 3. So that makes this point right here a node. We'll call that point B. When we have the same situation here, wire 3, wire 1, that would also make, we'll call this point, I don't know, A, a node. So points B and A are nodes. And the current law states that the sum of the current going in equals the sum of the current that goes out. Now, the direction of current that you choose is arbitrary, meaning basically I can BS it. But as long as you are consistent, it does not matter what direction in which you choose it. Okay? Now, I typically, when I choose the direction of the current, always start from the source of potential, which is way over here and way over here in this problem. I always start from the source of potential and work my way around because, honestly, it's easier. It's easier for me to start from the source of potential. You do not have to. There's no obligation to do this. But it makes your life and mine easier when you do start from the source of potential. When you have that option. There are situations where you may have a situation just all resistors, and then you can't start from the source of potential. Okay. But if you have a battery, or a source of potential, it's always easier to start from that particular point. So, some rules of convention are needed. Okay. So with a battery, here's your battery. The 4 lines form the battery. I know some books use 2, but because a capacitor looks similar as far as its schematic notation, I like to use 4 lines instead of 2. Okay. This is your positive terminal, and this is the little one is your negative terminal. Now, if you're going from the region this way, if your eye is going that way, from the negative to the positive, we define that to be positive potential. We define that to be a positive current. We're going to define it to be positive. Okay? And eventually you'll learn that that this is also defining a positive potential difference. Okay? And then I'm going to define the other direction, the opposite direction. Here, 1, 2, 3, 4, plus, minus, going from the region without electrons this way, I. This is going to be a negative current. I'm going to define it as a negative current. And let's just easier. And since I always like to use positive currents, it makes my life easy. Okay? So when I'm dictating how this works, the sum of the current going in equals the sum of the current that goes out. Okay? So how does this work? So in this situation here, I have a current that's coming in here. I'm going to call that I1. Okay? Because I'm starting from this positive end. And this is the way I usually go. I usually start from the positive end and go this way because that will, as you'll learn, will be a positive potential difference. Okay. Okay. And then, alright, now, in this situation here, it doesn't really matter, again, what I do. I could say, now, starting again from the same source here, I'm going to go like this. So I like to be consistent in which way I'm going. In this situation, I'm going clockwise here. So that's going to dictate that this goes down here, I2. And because I'm dictating that to be down, because I'm dictating I2 to be down, even though I don't know whether it will officially be or not until I analyze the circuit. Okay. Because that dictates I2 down, I'm going to dictate that I3 comes this way. So I'm going to go here counterclockwise. So it's coming in like this. So I3 is going to come like that. Okay? And so the way I stated the current law, I stated it that the sum of the current going in is equal to the sum of the current that goes out. And I stated it this way for a reason. Okay? I stated it this way so that you don't screw up the signs when you plug in the numbers. Okay? I stated this way so you don't screw up the signs when you're working with these types of problems, because the other way it's often stated that the sum of the currents at the node must be 0. But as you can see, I have dictated for you kind of the positive and the negative currents. So in the case of my currents that go in, I1 and I3, okay, and then the current that goes out is I2. Just I2 by itself. But there can be other situations where you have multiple currents going out, but those are more complicated problems, obviously. Now, if I take and move I2 to the opposite side, this ends up being I1 minus I2 plus I3 is equal to nothing, which is the same thing stated differently. So you can see here, in the first situation, here I have a positive current because this is coming this way, and then I have again positive current coming this way, positive current coming that way, and then I'm going to have the negative current coming from I2. Why? Okay. Well, I2 is going outwards. And you'll learn later that this is all arbitrary. That this is just dictated. That this is just dictated. You kind of make it up. And then as you get better at analyzing circuits, you'll guess correctly the first time the direction of the current, because that will dictate other things. So you have to start by getting the direction of the current before you do anything. So before you work with this voltage law, you have to get the current law correct, or you have to get the current law stated. Okay. because that's going to dictate what you do with the voltage law. Okay? You got it? Let's move on. And then, so to state this mathematically, I'll put it right here. The sum of the current going in is equal to the sum of the current that goes out. Okay? This is mathematically, it's stated. And then Kirchhoff's voltage law, which is probably a lot more familiar to you, which simply states that the sum of the voltages in a loop are 0. Or mathematically, delta U, sum of delta U is equal to 0. I use delta U for potential difference versus V. The reason being V is also used for voltage, and I'm part Russian. So, by inheritance, quote unquote. But since U is used by Russian oftentimes enough for potential difference, I copied it. And it's because also the units for voltage are used V, so I just use U to differentiate between the the concept of energy potential difference and the unit's voltage. Okay. Now, going back to my wonderful diagram here. As I've told you, the direction of the current dictates the voltage situation. Okay. I'm going to use a different color here to point that out. Okay. Now, in the same situation here, I dictated that this is a positive current and a negative current. Alright, this is going to be the same here. This will be a positive potential difference, and over here on this side will be the negative potential difference going back. And some people ask me, how did you know to do that? Alright, it should make sense to you, because there's already negative electrons on this side of the battery. So, if you're going from positive, you're stacking the deck. You're stacking the deck in this way. So, if the current's coming from this direction, you're stacking the deck, which is why it ends up coming out negative here. Okay? In this situation here, you're not stacking the deck. You're trying to even out the deck, because all the electrons are on this side of the battery. So it's therefore positive. Okay, that's why we dictate that. Because it really doesn't matter as long as you dictate, as long as the dictations are correct. As long as you keep the algebra good, it doesn't matter what the heck you do or how you state it. Okay? Now, the rule, of course, for the voltage law is that voltage decreases when you leave the battery in the direction, when you leave in the direction of the battery. Okay? So this is kind of a trick rule here. So if I was to set up the voltage law for this particular example, okay, for this particular example, I start with the source of potential difference for each loop. I can call this loop 1, I can call that loop 2. As long as I form a closed path, it forms a loop. There's actually 3 loops in this problem, but we ignore the third one, which is the entire thing because it's a redundant statement. So, if I'm starting with the potential difference, in this situation, I'd make my delta U positive. Okay. I normally use delta U also as my source of potential. I forgot to mention that. To differentiate that from potential energy, because delta U, potential difference, always refers to 2 points. So I make the delta U to make that connection between those 2 points. So if I start here, Okay. Now again, you would have to you would simplify this circuit before you do anything. Okay. And this actually will end up being I4 here. I4, so it's I1, I2, 3I4, and since it being plus I4, I missed that when I did this problem, but that's okay. Now, starting from here, right, since the voltage will decrease here, decreases here, so going from this way, this will be minus delta U at the resistor, which will just simply be I1R here, and then we're going to go again with, since we're going with the current, dictated with the current, again, it goes like that. So it's going to be minus I2R minus I4R. I'm not actually going to do this example. I'm just showing this for you just to set up purposes. Okay. Why is everybody minus? Because in each situation, we're going with the current. Okay. Now, as I said before, everything is dictated by what I do here. I dictated that this way I would go counterclockwise. By the way, these two will have the same current. Why? Because they're in series. So the current does not divide between the two of them. So this one will have the same current as this one. So for loop 2, I set it up this way. Negative delta U sub 2. Why? Because in this situation, we're stacking the deck. We're going, okay, it's negative in this situation because 1, we're going counterclockwise, but 2, right? See, we're coming out the negative end here. We're coming out the negative end of the battery. So we're stacking the deck. So this is against negative. Okay? So what does that do to the sign? What does that do to the sign? Okay. And this one. Okay. Again, we're with the current in the situation here. Alright? Now, see, the current is going this way. So, because we're with the current, it's going to be minus I3R. And then, again, same situation here. We're with the current in this situation. And this is just an example. So again, we're going with the current here. Now, I could have done this. Let me erase this. I could have dictated that the current go in the opposite direction here for this problem. I could have dictated this. It could have dictated that the current go this way. Okay. Which, by the way, would change this to I3 and I2. Okay, which would change this. It does not change I4. It does not change I4 because that one's already going this way. So if I dictated it this way, okay, I start with the positive potential, positive delta U because it's coming out the positive end. Okay. 9 is now it's opposite in this situation here. It's opposite the dictated direction of the current, right? Because these two cannot contradict each other, right? They cannot contradict each other. So one of them has to be wrong. So in this situation, it is not negative, it is positive I2R. Because I dictated that current already. I dictated it that it go this way. If I dictated it to go this way, it has to be positive. Okay? So going up. Right? So this is probably a better way to do that. Okay? Now, in this situation, again, we're going with the directed current, so it's going to be negative. And then again, we're going with the current, so it's going to be. Alright? So that's just how we set it up, kind of. So the idea being is that this all adds to 0. And I'm just doing this to set it up, just to show you how to set it up, kind of. So the idea is that everything adds to 0, but it's all dictated by the direction that I give the current. So I was yapping my mouth for a lot of time. So instead of yapping my mouth, I'm going to show you how to do this problem. Yeah. So that looks kind of ugly. Let's just go to another page and let's do a different problem. Let's set it up. Okay. So if I have a circuit, something like this. Call that delta U1. This is delta U2. This will be R1. It'll be R2. I can never really draw these things sideways, so you just have to narrow that in R3. So here's our problem. We have given delta U1 is equal to 6 volts. Delta U2 is equal to 9 volts. R1 is equal to 2 ohms. R2 is equal to 1 ohm. R3 is equal to 4 ohms. Then I want to find a couple things. So I want to find the current, I want to find the potential difference at each resistor. I want to find the current at each resistor. And I want to find the power at each resistor. This is actually slightly different than what I'm doing. Slightly different than what the book example that I'm using it from is. So it's a little bit more complicated. Okay. So the first thing I want to do is, of course, assign a direction to the current. So the first thing that we're going to do to solve the problem is to assign a direction of the current. We need to assign a current direction. It does not matter in which way I decide to do it. I, as I always told you, started from the potential difference and worked my way accordingly. So let's draw our circuit. There's R1, R2, R3. Now how do I dictate what do I do? delta U1, delta U2. I always start with the source of higher potential difference. So in this case, I'm going to start with the 9-volt battery and not the 6-volt battery. And you may ask, how did I know to do that? You don't. You can kind of dictate whatever way you want, as long as you're consistent. Okay? Now, because I'm starting with the high... Oops, I drew the direction of the second battery wrong. This should be facing the other way. And actually, the direction of the battery has a lot to do with the problem. The direction of the battery has a lot to do with what I want. Okay. So, since I'm going to start with the source of higher potential difference on the higher battery, that will dictate what I do. So it dictates the fact that I'm going to direct the current to go this way. So I'm going to dictate this for the sake of simplicity. I'm going to dictate this to be I3, and the reason why I'm going to dictate it to be I3 instead of I1 is because I just find it's just easier to match the current to the resistor, even though you're not always going to have this luxury option. So it's going to dictate this way. So it's going to go this way, and thus dictating I2 to come up. I2 will come that way. Now, that's just for loop 1. So this is going to be our loop 1, and this will be our loop 2. So for loop 1, I've dictated I3 to go this way, and I1 to go this way. And then for I2, it's a separate situation. Loop 2 is a separate situation. I can dictate the current to go whatever way I want. Again. Now, I like to go... So I like to go from the positive and out because it makes my potential difference positive. So I'm going to go this way, down, for I1. And then I'm going to end up with a contradiction of I2. Okay. Even though I don't have to do it this way. Okay. But actually change that thought. I want to go the other way. And you may ask, how did I know to go the other way? You don't. It's arbitrary. It's very important to recognize the direction of the current is entirely arbitrary. Okay. But I'm going to send it this way for no other reason other than I feel like it. And then to have this lead to I2. I2 is already dictated, so you don't need to redo it. Okay, and I'll explain why. I2 is already dictated this way. So I'm going to go around this way, and then I1 will come up this way like that. Okay? Everybody got it. So we have a node that forms here. We'll call that point A. So it's at point A. So now that we've formed the node, we can dictate the current law. Okay. Since I1's going out, I2 is, and so then I3 comes in. I3 comes in, I1 and I2 go out. So there's a sum of the current in equals the sum of the current out. I2 goes in, I1 and I2 go out. So when I3 is equal to I1 plus I2. Everybody good? Now that we've dictated that point, we can now use the potential difference law. Okay, so now that we've set on the current, now we're going to use the voltage law. So step 2 is to use the voltage law. Alright, starting with loop 2, because it's the one I began with. Okay. I'm going to start from my source of potential difference. Alright, going out the positive end, so it's going to stay positive. So the sum of potential differences equals 0. Positive delta U2, that's what I dictated here. And this ends up being minus I3 R3. And again, I'm going with the current, so it's going to be minus I2 R2. Okay. And that all equals 0. And normally when we do electric problems, circuit problems, we just plug the numbers in right away to make our lives easier, because solving it symbolically is so I can just plug it in straight from here. I know that this is 9 volts minus R3, which I dictated to be 4 volts, right? Yep, exactly what I did. So 4 ohms, sorry. So 4I3. And of course, mathematical convention dictates that we put the coefficient up front. And of course, R2 is 1, so it's just going to be minus I2 equals 0. And you can leave it like that if you want. Okay. Alright, so with the current, so we went with the current in this situation. Now, okay, got it? So that's this one. And if I want to solve it for this, I can do like that. I can say I2 plus 4 I3 is of course 9. Okay. And then now for loop 1. And of course, going back to my picture here, loop 1, I decided to go the other way. I decided to go clockwise for loop 1. I actually decided to go clockwise for both directions, oddly. Here. And since I decided to go clockwise here, for loop 1, of course, we remember sum of potentials is equal to 0. Negative delta U sub 1. Why? Because again, we're stacking the deck. We're stacking the deck in this situation. We're putting more electrons where there's already enough electrons, so that's why the current will be negative. And then will be plus I2 R2. Why plus? Because we're going against the current that we dictated in loop 1. So see how we're going this way here? We're going against the current that we dictated this way. That's why I told you I only need to do the current once instead of twice, because we're going against the directed current here. Okay? And then going counterclockwise again around this. And now we're going back with the current so that we minus I1. So this will be minus I1, R1 is equal to 0. Plugging in the numbers, negative 6 plus I2, of course, minus 2 for 0. We can solve it. This ends up being I2 minus 2I1 is of course nothing. Is of course positive 6. Then the next thing we want to do is set up a system of equations for our problem here. So these three, we set up the system. So the system of equations dictates, we have two of them. So we have I2, it's 4I3, equals 9. The second equation is I2 minus 2I1 is of course 6. Now, I have a problem. I have 3 unknowns and 2 equations. How do I get rid of this third unknown? The third unknown can be eliminated via elimination or substitution. So we can eliminate it via substitution. Substitution dictated earlier that I3 at node A, okay, because I3 goes in, I1 goes out, I1 comes out, and then I2 goes out. And so that's how we got this nest here. Okay, so it's I3 is I1 plus I2. So we're going to go back here and plug that into the equation. So I2 plus 4I1 plus I2. Make sure you're very careful when you're doing substitution. Make sure you keep your signs straight and don't screw that up, because it really does make a difference. And in the situation here is of course 9. Distribute the 4. 4 times 1 is 4. 4 times 1 is still 4. 4 plus 1 is of course 5. So it's going to be 5I2 plus 4I1 equals 9. I2 minus 2I1 is equal to, of course, 6. Now, from here, it's just a matter of mathematics, recognizing where you are. So, multiply by 2. So, multiply everything by 2. So, dictate, dictate, dictate. And so, if you multiply by 2, we get 4 here. So I'm going to show you that step even though I don't have to. Plus 4I1 equals 9. 2 I2 minus 4I1 equals 12. Okay? Got that, everybody? And so from here, we do some algebra. This ends up being 7. I1, I2 is equal to 21. And then we divide, of course, by 7. Divide by 7. Divide by 7. I2 is equal to 3 amps. The units for current are amperes, and of course you know the rules. We put parentheses around the units because we didn't use them in the calculations. So I2 in this situation is 3 amps. And it's positive, meaning we got the direction of I2 correct. Okay. And so it's positive because we got the direction correct. Now we need to go back and solve this equation, of course, for I. So we need to go solve it for I1. So it doesn't matter what equation I choose. So let's say I choose the bottom equation here. Simply solve it for I1. So I know that twice I1 is equal to I2 minus 6. I2 is 3. So this becomes 3. So this ends up being negative 3 twice I1. Divide by 2. Divide by 2. I1 is equal to negative 3 halves of an amp. And why is it negative in this situation? It's negative because I guessed wrong on the direction for I1. It means I guessed incorrectly for that direction. That particular direction, it means that I guessed wrong. And of course, I1 plus I2 is I3. And so I3 is equal to I1. And always remember to keep the algebra consistent here. So you have negative 3 halves plus 3. So that's going to be negative 3 halves plus 6 over 2, which is of course 3 over 2 amps. Okay. So I3 is going to be 3 over 2 amps. Okay. So now that we know that, so now that we figured out the current at each resistor, go back, look at the I3 here is 3 halves of an amp. The positive direction. This one here is 3 amps. And then this one's also, this is negative 3.5 amps. Okay? So far so good. So when I do this, so I like to set up tables. And so we know this is the resistance in ohms, potential difference in volts, and of course the current, which is in amps. And of course we have the 2 ohm resistor, the 1 ohm resistor, and the 4 ohm resistor. And so therefore, we found that I2, this is R1, of course, when we labeled it R1, R2, R3. we found that I2, which belongs to this one, was 3 amps. This was negative 3 over 2 amps. And this is positive 3 over 2 amps. And if I add the current together, sum of the current in equals the sum of the current going out. It works. It's legit. Okay. And if I multiply, of course, current times resistance, I'm going to get the potential difference for each point. So 3 times 1 is, of course, 3 volts. 3 times 2. Negative 3 times 2. Negative 3 over 2 times 2, which will, of course, be negative 3 volts. And then 3 times 2. Then 4 times 3 over 2 is, of course, 6 volts. And that works for both problems. And that actually works here because the total current, right, the total voltage, back in our problem here, we have 9 volts in the first battery and 6 in the other. Here's these two get our 9 volts, and if I take those two away, I get the 6 volt battery. So it works out perfectly. Okay? And then for the power, I take, of course, current times potential difference for each one. So current times potential difference. Current potential difference. So negative 3 halves times negative 3 is going to be negative 9, or positive 9 over 2. Oops, I'm sorry. Power is in watts. The only American to get a unit named after him, go figure. So, and then this is in watts. And then 3 times 3 is, of course, 9. And we can do, this will also be 9 watts. And that's the problem, and that's how you do it, basically. Okay. That was a relatively simple problem, and I broke it down. It's always easy to take a complex problem and to break them into pieces, rather than to try to attempt to solve it all at once. Okay. And next time I want to do a different problem. And look at it from a different perspective. And I want to do another problem which we'll look at from a different perspective. Okay. That's how we do that problem. And these match the answers that are in the book. So good job, us.